Hi, today's lecture is about the atoms theory. So we're going to see the early ideas of atomic theory. And yeah, let's talk about the roots of the atomic theory. So science, as we know it today, did not exist several thousand years ago. No one knew that a controlled experiment was, and there were few tools for scientific exploration. In this setting, the power of the mind and intellectual thought were considered two primary avenues to the truth. Curiosity sparked interest of scholarly thinkers known as philosophers, who consider the many mysteries of life. As they speculate about the nature of matter, many of the philosophers formulated explanations based on their own life experience. And here we can see, for example, a fresco. Okay, this is a fresco. A fresco is a kind of paint that is made on a wall. And particularly this one is the Raphael's masterpiece, the School of Athens. Okay, Raphael Sanzio was already a star by his mid-20s. At the top of his game, this master of the Italian Renaissance had been invited into the Pope to live in Rome, where he would spend the rest of his days. Starting in 1509, he began decorating the first of 4 rooms in the Papal Palace. Collectively, these Raphael rooms, along with the Michelangelo Sixtine Chapel, let me see, is an example, an example of the high Renaissance fresco technique. Okay. In particular, Raphael's fresco, the School of Athens, has come to symbolize the marriage of art, philosophy, and science that was a hallmark of the Italian Renaissance. Painted between 1509 and 1511, it is located in the first of the 4 rooms designed by Raphael. It's called La Stanza della Segnatura. La Stanza della Segnatura. Y La Stanza della Segnatura is the following picture over there. Okay, look at this, it's beautiful. Okay, here is the principal fresco, and this room over here. Okay, and yeah, if we want to talk about the Stanza della Segnatura, yeah, first of all, here we can see set in an immense architectural illusion painted by Raphael. For example, the figures of the principal philosophers at that time. For example, we can see here Plato and Aristotle. Plato and Aristotle. Here we have Plato left, Aristotle right, at the center of the fresco, right? Okay. Also, we can see Socrates. Socrates is this guy over here, okay? This guy over here is Socrates, Plato, Aristotle, Socrates, okay? Okay, let me see. Oh, yeah, Pythagoras. Pythagoras is this guy with the book right here, okay? This is Pythagoras. Okay, is Pythagoras sits with the book, okay, also surrounded by students. Euclid, Spanish Euclides, okay, Euclid is known as the father of geometry, okay, the father of geometry. And we can see Euclid right here, yeah, with a compass, okay, excellent. Let me see. Oh yeah, Ptolemy. Ptolemy here is with the terrestrial glove in his hand. This is Ptolemy. Okay. Very good. And yeah, of course, for example, picking out at the viewer is none other than Raphael himself. Okay, let me see if I can show you. Where is Raphael? Yeah, here next to Ptolemy. Okay, that is Raphael. And Diogenes. Diogenes, at Spanish, Diogenes. Okay, Diogenes or Diogenes. Okay, it is universally agreed that the older gentleman sprawled onto the step is Diogenes, the founder of the Cynic philosophy. He was a controversial figure in his days, living a simple life and yeah, is going he didn't like the cultural convention at his time. That is Diogenes or Diogenes, right? Okay, let me see. Oh yeah, the statue, we have two statues. Statue on left is, let me see, on the Plato's right, that is Apollo. Okay, Apollo, this is Apollo. Let me see. This one is Apollo. Okay, and this is Minerva. Two statues. Oh yeah, of course. And this lady over here is oh my God. This lady here is a philosopher, yeah, right? Oh, I forgot. 1 second. Yeah, right. Now, Hypatia. Okay, Hypatia was a woman on the 3rd century after Christ. Okay, she was a philosopher and also scientist because she almost discovered Jupiter 1,200 years ago, from before Galileo's did it. Okay, So she was incredible. Okay. Yeah, this is Hypatia. Okay. So if we're going to talk about the philosophers, of course, that many philosophers conclude, for example, Aristotle conclude that matter was composed of things like earth, water, air, and fire. Okay? The four elements: earth, water, fire, and air. This was the principal idea from Aristotle. But first, if we can talk about philosophers, of course, I will begin with Democritus. Okay? So, Democritus was 400 years before Christ and was the first person to propose the idea that matter was not infinitely divisible, okay? Or divisible. Yeah, it's divisible. He believed matter was made up of tiny particles called atoms, from which the English word atom is derived. Democritus' model states that matter consists of invisible particles called atoms and a void, yeah, an empty space. He stated that atoms are indestructible and unchangeable. Also, that they are homogeneous, meaning that they have no internal structure. And his atomic model was solid and stated all atoms differ in size, shape, mass, position, and arrangement, with a void exists between them. That was Democritus. After Democritus, Empedocles devised the theory that all substances are made of four pure indestructible elements: air, fire, water, and earth. In one sense, it is admirable that Empedocles tried to simplify our complex world into basic elements. And Aristotle's idea, of course, is that did not believe in the atomic theory of Democritus. Okay? He thought that all materials on Earth were not made of atoms, but of the four elements: earth, fire, water, and air. He believed all substances were made of small amounts of these four elements of matter. Those are the philosophers, okay? And yeah, the problem here is that Aristotle, okay, let me see, I can show you. Okay, Aristotle, he rejected the notion of atoms because he did not agree with his own ideas about nature. One of Aristotle's major criticisms concerned the idea that atoms move through empty space. He did not believe that empty space could exist. His ideas also, okay, presented on the PowerPoint presentation, okay, because Aristotle was one of the most influential philosophers of his time. Democritus' atomic theory was eventually rejected. Okay. In fairness to Democritus, it was impossible for him or anyone else on this time to determine what held atoms together. More than 2,000 years would pass before scientists would know the answer. However, it is important to realize that Democritus' ideas were just than ideas, not science. Without the ability to conduct control experiments, Democritus could not identify patterns. Okay? And that's the principal fact why philosophers like Democritus, for example, they are not scientists. Okay? Unfortunately, for the advancement of science, Aristotle was able to gain wide acceptance for his ideas, right? Was Aristotle the most famous philosopher at his time? So, incredibly, the influence of Aristotle was so great and the development of science so primitive that his denial of the existence of atoms went largely unchanged, unchallenged for 2,000 years. So we need to wait 2,000 years. And a guy called John Dalton here, okay, John Dalton was the first scientist that thought about the atomic theory. Okay? So Dalton, although the concept of the atom was revived, okay, in the 18th century, it took another 100 years before significant progress was made. The work done in the 19th century by John Dalton, that is from 1766 to 1844, after Christ. John Dalton, a school teacher in England, marks the beginning of the development of modern atomic theory. Okay? Dalton revived the Democritus idea based on the result of scientific research he conducted. In many ways, Democritus and Dalton ideas are similar. Thanks to the advancement in science, since Democritus' day, Dalton was able to perform experiments that allowed him to identify patterns that refine previous understandings and develop new explanations that were supported by his research. Okay. He studied numerous chemical reactions, making careful observations and measurements along the way. He was able to determine the mass radius of the elements involved in these reactions. The mass radius describes how many atoms of each element make up a compound The result of this research are known as Dalton atomic theory. Okay. And look at this. For Dalton, an atom was a ball, right? Yeah, without charge, without protons, without electrons, and without neutrons, like today's atom looks like, okay? So for Dalton, atom was just a ball. And as solid as sphere, he proposed his theory that atoms are small and indivisible, okay? Can't be divided, created, or destroyed. An element is identical. Different elements, okay, that means different properties. Atoms of different elements combine to form compounds. And we have here the 4 statements on Dalton atomic theory. Okay, so number 1, each element is composed of extremely small particles called atoms. An atom of the element oxygen and an atom of the element nitrogen, okay? All atoms of a given element are identical, but the atoms of one element are different from the atoms of all other elements. So, yeah, all oxygen atoms will be the same between them. And yeah, you can differentiate from nitrogen. Atoms, number 3, atoms of one element cannot be changed into atoms of a different element by chemical reactions. Atoms are neither created or destroyed in chemical reactions. So we cannot change an oxygen atom into a nitrogen atom. Okay, that's a shame for the alchemists, right? Because alchemists want to create gold from other element or other metal. And yeah, you cannot do that. Okay, you cannot convert aluminum into gold. That's impossible. 4, compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. Okay, so if you mix nitrogen and oxygen, okay, you can form a nitrate, for example. And this gives us the conservation of mass, okay? The law of conservation of mass states that mass is conserved in any process, okay? Dalton's atomic theory explained that the conservation of mass in chemical reactions is the result of the rearrangement of atoms during the reaction. They are not created or destroyed, okay? And the formation of a compound by combining elements is shown in the next figure, okay? So, for example, if we have atoms of the element A, the total mass is 4, and atoms of the element B, we have 2. If you combine together, you can form, for example, water. This can be water, okay? Water is 1 oxygen and 2 hydrogen. next to the oxygen, okay? Excellent, this is the conservation of mass. So Dalton's convincing experimental evidence and clear explanation of the composition of compounds and conservation of mass led to the general acceptances of his atomic theory, okay? And this is very important. He did experiments to demonstrate the theory, okay? That is very important. Okay? The total number of atoms of each element is the same before and after the reaction. Very good. So the atom, okay. So the atom. So what exactly is the definition of an atom? To answer this question, okay, consider a gold ring, okay? Suppose you decide to grit the ring down into a pile of gold dust. Each fragment of gold dust still retains all of the properties of gold. If it were possible, which it is not without the special equipment, you could continue to divide the gold dust particles into still smaller particles. Eventually, you would encounter a particle that could not be divided into or any further and still retain the properties of gold. This smallest particle of matter that retains the properties of the element is called an atom, okay? How an atom looks like. Okay, I can show you. For example, these, okay? These pictures over here is the scanning tunneling microscopy. Okay, the development of the family of scanning proof microscopes start with the original invention of the STM, the scanning tunneling microscopy, okay, in 1981. Okay, for example, let's see the image, green, blue, and yellow from the left. Okay, this image shows the direction of standing wave patterns in the local density of states of the copper. Yeah, there is a copper surface. And yeah, it's standing wave patterns. At the end of this class, we're going to talk about Schrödinger's atomic model, okay? Yeah, atom is a wave, standing wave pattern, okay? You can see only the standing wave pattern. Use statistics to describe the atom. That is quantum mechanics, okay? This spatial oscillation are quantum mechanical interference patterns caused by scattering of the two-dimensional electron gas of the iron atoms and point defects. So yeah, it's a little bit complicated, but it's quantum mechanics, and quantum mechanics, believe me, is a hard topic to talk about this at this level. But yeah, we're going to talk about that maybe in some years from now, here in class, obviously. Okay, so how the STM works. Okay, the scanning tunneling microscope works by scanning a very sharp metal wire over a surface, okay? And you can see the principle, yeah, the image from right, okay? For example, we can see, let me see, we can see like yeah, let me see if I can, yeah, it's like a relief. Let me see if I can see, no, yeah, the relief, yes, the relief of the surface of atoms that we have to do the STM, for example, okay? But actually, you're not looking the atom, you're looking the wave pattern, okay? The standing wave pattern, okay? We can visualize, let me see. Visualize, yes. Yes, we can visualize the relief of the cloud electrons of the atoms, okay? And the computer formed the standing wave pattern. Yeah, it looks complicated, but is the most realistic form, the most realistic form that we can visualize the atom, okay? So it's perfect, it's perfect. After this, okay, for the to define an atom, we can talk about the first subatomic particle inside a nucleus, okay? And here, of course, that we can talk about the electron and J.J. Thomson, okay? So the electron, one scientists were convinced of the existence of atoms, a new set of questions emerged. What is an atom like? Is the composition of an atom uniform throughout, or is it composed of still smaller particles? Although many scientists researched the atom in the 19th century, okay? And it was not until almost 1900, or the beginning of the 20th century, that some of these questions were answered. Okay, the development of new technologies allowed scientists to develop models that were used to simulate systems to determine interactions within and between systems at different scales. And here we have the cathode ray tube, okay? The cathode ray tube, I can show you, okay? This is the cathode ray tube. As scientists tried to unravel the atom, they began to make connections between matter and electric charge. Scientists learned through experimentation using models to simulate systems that the structure of interaction of matter are determined by electrical forces, okay? With the help of the newly invented vacuum pump, they passed electricity through glass tubes. from which most of the air had been removed. Such tubes are called cathode ray tubes and were invented and investigated by scientists from 1869 to 1875. Okay, a typical cathode ray used by researchers for studying the relationship between mass and charge is illustrated in this figure. Okay, note that the metal electrodes are located at opposite ends of the tube, and the electrode connected to the negative terminal of the battery is called cathode, and the electrode connected to the positive terminal is called anode. Okay, the anode is connected to the positive of the battery, and cathode is connected to the negative pole in the battery. Okay. Sir William Crooks, okay, Sir William Crooks, while working in a darknet laboratory, English physicist William Crooks noticed a flash of light, okay, a flash of light like this green light over here, a flash of light, okay, within one of the cathode ray tubes. A green flash was produced, okay, by some form of radiation striking a zinc sulfide coating that had been applied to the end of the tube. Further work showed that there was a ray of radiation going through the tube. This ray, originating from the cathode and traveling to the anode, is called cathode ray. Okay, this is a cathode ray. The accidental discovery of the cathode ray led to the invention of television, for example. Okay, look at this, which is nothing more than a cathode ray tube. Scientists continued their research using cathode ray tubes, and they were fairly convinced by the end of the 18 years, okay, the 19th century, at the end of the 19th century, that cathode rays were a stream of charged particles, and that these particles carried a negative charge. The exact value of the negative charge was not yet known, because changing the metal that makes up the electrodes and varying the gas, a very low pressure, in the cathode ray tubes did not affect the cathode ray produced. So researchers conclude that the ray's negative particles were found in all forms of matter. These negative charged particles that are part of all forms of matter are known as electrons. Okay, so electrons. And the first subatomic particle was identified by J.J. Thomson, and he received a Nobel Prize in 1906 for his discovery. Very good. This is J.J. Thomson. Okay. Using the Sir William Crooks cathode rays. Okay. So, yeah, of course, J.J. Thomson proposed atomic model. Okay. And this atomic model is the Plum pudding model. Okay. The Plum pudding model. Because it's like a pudding. Yeah. The mass of the pudding will be the positive charge. And the plum, yeah, each plum is like an electron, okay, that is glued into the positive charge. So let's see the Plum pudding model, okay? The Plum pudding model, the existence of the electron and the knowledge of some of its properties raised some interesting new question about the nature of atoms. It was known that matter is neutral. It has no electric charge. So if electrons are part of the all of matter, sorry, if electrons are part of all matter and they possess a negative charge, how can all matter be neutral? Yeah, in attempt to answer this question, J.J. Thomson proposed a model of the atom that became known as the Plum pudding model, okay? And consists of a spherically shaped atom composed of a uniformly distributed positive charge in which electrons reside. Okay? So he found that an atom consists of the positive and negative charge. An atom is electrically neutral, okay? Positive and negative will be in the same quantity in an atom. And negatively charged electrons are fixed in the positive sphere, okay? This is the Plum pudding model. Very good. But yeah, a new scientist arrived here, and it is Ernest Rutherford, okay? Ernest Rutherford was from New Zealand, okay? Began to study how positively charged alpha particles that are radioactive particles, okay, interact with solid matter. With a small group of scientists, Rutherford conducted an experiment to see if alpha particles would be deflected as they pass through a thin gold foil. If they were deflected, by how much would they deflect? This is the question, okay? And look at this. Okay. The Rutherford experiment, okay? Let me see, I can show you. I can show you here, okay? In the experiment, a narrow beam of alpha particles was aimed at the thin sheet of gold foil, okay? A zinc sulfate coated screen surrounding the gold foil produced a flash of light when struck by an alpha particle. By noting where the flashes occurred, the scientists could determine if the atoms in the gold foil deflected the alpha particles. As with any good experimental design, the procedure was repeated over and over again to ensure that all observations were taken and that all results observed were repeated in each trial, okay? As the number of times an experiment is repeated increase and the same results are obtained, the results, of course, are easier for scientists to accept. Rutherford was aware of Thomson Plum pudding model of the atom he expected, I will show you this. This is important, okay? It's very, very important. So, yeah, so sorry, this is out of the screen, okay? So I can show you with an animation here, okay? Come on, let's see this. Okay, this is the Plum body model from J.J. Thomson. Okay, Rutherford expected the path of the massive and fast-moving alpha particles to be only slightly altered by a collision with an electron. Okay, so he expected that the alpha particles, okay, pass with a little altered path by the J.J. Thomson atomic model, okay? And because the positive charge within the gold atoms was thought to be uniformly distributed, he thought it would not alter the path of the alpha particles either. So this animation shows the results Rutherford expected from the experiment. If the J.J. Thomson model was right, you can see this on the experiment. Okay? The actual results observed by Rutherford and his colleagues actually is not this. Okay. Okay, let me see. I can show you. Actually, is this one. Okay. Okay, so no, let me see. Let me show you. Let me show you this one first. Okay. Yeah. This is the actual result observed by Rutherford and his colleagues. Some alpha particles were deflected at various angles. Several particles were deflected straight back toward to the source. Rutherford liked the results to firing a large artillery shell at a sheet of paper and the shell coming back at the cannon. Yeah. And yet this is the principal idea, or this is the principal fact that atoms, can have a positive nucleus, okay, that J.J. Thomson didn't propose on his model, okay? So the Rutherford's model of the atom conclude that the Plum pudding model was incorrect because it cannot explain the result of the gold foil experiment. Considering these properties, okay, considering these properties of the alpha particles and the electrons and the frequency of the deflections, he calculated that the atom consisted mostly of empty space through the electrons move. He also concluded that almost all the atom's positive charge and almost all of its mass were contained in a tiny dense region in the center of the atom called the nucleus. Okay, so this is the, this is the Ernest Rutherford nuclear model, okay? So atoms are mainly empty space and positive charge is concentrated at the center of the atom, the nucleus. The center of the atom will be the same as the nucleus, okay? And the electrons move around the nucleus, okay? This is Ernest Rutherford model. And the animation that I will show you, yeah, is this one. So here, okay, here we have the nucleus. I will through alpha particles, and you can see thanks to the positive charge of the nucleus, okay, why alpha particles go away from the nucleus. Yeah, because alpha particles have positive charge, and nucleus also has a positive charge. And remember, this is Coulomb law. Coulomb law tell us about the repulsion or attraction of two different charges, okay? If we have two positive charges near one for another, they will feel a repulsion, okay? They will not touch together, okay? So yeah, this is the experiment. This is the Rutherford experiment to demonstrate the existence of the nucleus, okay? And we can see here in the gold foil, for example, of different gold atoms, how the alpha particles scattering from the principal or the initial trajectory that they have, okay? Okay, very good. This is the Rutherford experiment. Okay. So, yeah, the negatively charged electrons are held within the atom of the attraction to the positive charged nucleus. So this is the let me see, this is the Rutherford nuclear atomic model, okay? Because the nucleus occupies such a small space and contains most of an atom mass, it is incredibly dense, okay? And yeah, the proton and the neutron, after the discovery of protons, by 1920, Rutherford concluded that the nucleus contained positively charged particles called protons, okay? So this is the principal discovery for Rutherford experiment, okay? Protons inside the nucleus. A proton is a subatomic particle, okay? Rutherford co-worker James Chadwick, come on, let's see, James Chadwick, okay, was a partner from Rutherford, okay, showed that the nucleus also contained another subatomic neutral particle called neutron, okay? So neutrons help to reduce the repulsion between protons and stabilize the atom's nucleus, okay? So neutrons are very important on the existence of the atom. Okay, so very good. And yeah, after this model, okay, after this model, Let me see. Yeah, we can talk about radioactivity. Yeah, radioactivity. So here on radioactivity, yeah, she is the big boss. Okay, Marie Curie. Okay, okay. In 1896, the French scientist Henri Becquerel discovered that the compound of uranium spontaneously emits high energy radiation. This spontaneous emission of radiation is called radioactivity. Okay. Yeah, we can see, for example, how was Henry Becquerel. Okay, this was Henry Becquerel. Okay, Marie Curie, after the Becquerel's suggestion, Marie Curie and her husband Pierre began experiments to identify and isolate the source of radioactivity in the compound. Okay, there are three types of radiation: alpha, beta, and gamma. Rutherford showed that the path of alphas and betas radiations are bent by an electric field, although in opposite direction. Okay, so for example here, okay, gamma radiation is unaffected by the field. Okay, they follow the straight line. But alpha and beta rays consist of fast-moving electrically charged particles. In fact, beta particles are nothing more than high-speed electrons charged that can be considered the radioactive equivalent of cathode rays. Okay, because of their negative charge, they are attracted to a positive charge plate, as you can see in the figure. And the alpha particles have a positive charge and are attracted to a negative plate. Okay, and the representation, okay, of alpha, beta, and gamma is in this paper. Okay, so alpha particles are helium atoms but without electrons. Okay, beta particles is one electron, just one electron, and gamma radiation is an electromagnetic wave. Okay, that's the reason why they don't feel the electric field, okay, when crossed between two plates, two charged plates. Okay, okay, excellent. Yeah, oh, I can show you here, for example, and yet these three particles are types of radiation, right? Okay, so for example, if we have a radioactive atom, we can see beta and gamma radiation when the atom is disintegrating. Okay, I can show you. Let me see, give me a moment, please. I can show you on the screen. One moment. I will arrive. Yeah, there it is. Okay. I can share my screen with you. Yeah, there it is. Okay, so the radiation and radioactivity, okay, as you can see here, for example, for the uranium 238 with a half-life of 4.47 billion years. So yeah, you have to wait 4.47 thousands of millions of years from the uranium 238 decays, okay, from or through the release of alpha particles. So if you have 1 kilogram of uranium 238, you will wait 4,000 millions of years to have only 1/2 of kilogram. And those are radioactive atoms, okay? Uranium, thorium, protactinium, uranium, radium, radon, polonium. Look at this. For example, the protactinium 234 that has a half-life of 6.7 hours, okay? Protactinium emits beta rays, okay? Emits beta. And uranium and thorium and radon emits alpha particles, okay? And look at the penetration of radiation, okay? This is incredible, okay? The penetration of radiation is the ability of different materials to block radiation and give us a clue to the nature of radioactivity particles or rays. For example, alpha particles, paper stops alpha particles. Beta particles, the plastic stops beta particles. But the gamma rays, only the gamma rays can stop is thanks to the lead piece, for example, okay? Lead stops gamma rays, okay? And yeah, we have here the alpha decay and the beta decay. The alpha decay, release of an alpha particle, removes 2 protons and 2 neutrons from the atomic nucleus. So its mass drops by 4 atomic mass units, while its atomic number drops by 2. But the beta decay, yeah, because beta is an electron, this decay involves a neutron in the atomic nucleus spontaneously changing into a proton. And atom mass is unaltered but its atomic number increased by 1. An electron is emitted, okay? Yeah, and we have here more. We have more here. Lead, bismuth, the polonium, okay? So, yeah, emits also beta and gamma. And finish with the atomic theory here. Okay, next is Bohr model, okay? We're gonna talk about this a lot. Yeah, we're gonna talk a lot of this model, but not in this lecture. The next lecture, we're gonna talk about Niels Bohr atom theory. Okay, this is the planetary model, okay? He said that electrons orbit the nucleus, okay? The orbits have different or a specific size and energy, and the energy is released to its size. The lowest energy is found in the smallest orbit, and electrons can move between each shell when gaining or losing energy. This is the planetary model. And yeah, we're gonna talk about why Rutherford nuclear model was incorrect, but we're gonna talk about this the next lecture. And the final atomic model is the Schrödinger model, okay? It's about the quantum mechanic model and works with statistics. and probabilities. Okay, so he discovered that the electrons move around the nucleus in a cloud, not orbits. Orbital help us to predict the area where we can find electrons. The closer position to the nucleus, the higher chance to find electrons, and yeah, higher probability to find one electron. Okay, but this is quantum mechanical model and works with clouds, probabilities, and a lot of math, a lot of math. So, to the next lecture, I will show you the two different models here, Bohr and Schrödinger. So, see you next lecture. Bye.